In a previous series of videos and blogs, we have been building a robotic car by designing, simulating, and analyzing our schematics using the power of Altair simulation. Be sure to check out those previous videos and blogs to get up to date on where we are currently. Today, we will work on using Altair Embed to analyze the feedback from earlier subsystems. Embed has many useful applications such as true hardware-in-the-loop testing, automatic code generation, and multi-physics simulation and co-simulation with various tools including PSIM. To begin this phase, we will use the software to generate a representative square wave in place of the output of the encoder. We can use a combination of the multiplication and summing junctions to scale the square wave to the same range as our real-world values, 2 volts to 5 volts. There is no noise in the simulated signal, but that is acceptable for our purposes, as we will only consider when the signal switches from high to low. To extract the useful information from this signal, we will implement a crossing detection block, and we will specify the crossover value to be the halfway point between the two extremes of the input signal, which is 3.5 volts. Normally, this block will produce a positive value if the signal is going up when it crosses 3.5 volts, and a negative value when it is decreasing through the crossover value. We are only interested in seeing one spike per cycle, so we will limit this output to remain positive. We will then use a variable block to save this signal as our zero crossing trigger, which generates a pulse for each whole cycle. Now we can design the period approximator. For this, we will take the zero crossing pulse train and introduce some new logic. First, we will use a sample and hold block with the pulse train and a ramp signal that increases linearly with time. In other words, the value of the ramp is equal to the current time relative to the start of the simulation. This will generate an output equal to the real-world time for each pulse of the trigger. Next, we will use the trigger again and the output of the sample and hold as inputs to the unit delay block. This will allow us to preserve the real-world time value from the pulse immediately preceding the current pulse from the trigger. With these pieces of information, we now have the time values for 2 consecutive pulses, and taking the difference between them will provide us with the time between them, which is equal to the period of our encoder signal. You will also notice that we add a very small value to the period and calculate the inverse. The small value is to ensure that we do not divide by 0 when inverting the period, which provides us with the measured frequency of the encoder wheel in Hertz. With a 15 Hz input signal, it is difficult to see the accuracy because the traces almost exactly overlap, but this means our frequency estimator is working as expected. We will add a display block to see that the estimated frequency is approximately 14.99 Hz, which is very close to the true value. We are now ready to implement this logic into the real-world device. We can do this by using the code generation capabilities of Embed to automatically create the code that will execute our design logic. The software will consider many aspects, such as the target device, which is the kind of microcontroller you are using, any inputs or output pins on the target device, which can be defined within the block diagram, and any custom logic implemented via block diagrams. Now it is time to test the code with an actual input signal. For this initial test, I provided an input of a 12 Hz square wave oscillating from 2 to 5 volts. Each line on the output is generated on each new rising edge, as defined in the Embed schematic. We can see that the estimated output is consistently very close to our true input, meaning this subsystem is almost ready for integration and deployment. We will also verify that our frequency measurement system can handle changes in the input. We can see that as we step through different input frequencies, our estimated output adjusts accordingly, ensuring that we can use this information as feedback in our control loop. The final step is somewhat trivial, but we will use a simple formula to convert the measured frequency to a measured linear velocity of the race car. The division by 4 comes from the fact that the encoder pattern is repeated 4 times per rotation of the tire. The diameter of the tire was measured to be 6.5 centimeters. With this information, we can find that the maximum linear velocity of the car will be approximately 77 centimeters per second. We now have all the pieces and information to power our drive system, measure its speed, and provide valuable feedback which will allow us to implement a control scheme and conclude the drivetrain portion of this project. Be sure to check out our blog and subscribe to this YouTube channel to get updates on this project and to learn more about what Altair has to offer. As always, please do not hesitate to reach out to us with any questions at trueinsight.io.